We're continuing our redo of the workshop slides. We closed the last piece with Challenger and how I became persuaded by Diane Vaughn's book that it was in fact a social failure, social context failure. That was an important revelation to me. I had sort of seen the same thing with Hubble. I was a member of the Failure Review Board as the NASA representative, but and it was kind of the same thing, but being in the middle of something versus reading a book about it's different. Let's take a look at what happened with Hubble. Interesting point. The early days of Hubble had a mug that I had one of the precious few originals which burned up in the house fire, no big deal. Conscious expectation of the unexpected was the motto when the project started. It was apt, but wasn't what we thought. So I go down to the launch, and normally when these big payloads launch, I'm in the VIP stands, and I'm talking with congressional people and things about next year's budget, this kind of thing, because the payloads are powered off during the ascent phase. I think it's been tested thoroughly. And the reason it's turned off is that the vibration is very, very high, especially the shuttle's main engines. One of the sort of problems with the design is the engines are right down next to the payload. And these big engines have what's called pogo. It's a oscillating effect that vibrates the payload really hard. So, but in the case of Hubble, there was a very specific issue. If we didn't get the right orbit during the ascent phase, and we all worried a lot about the shuttle main engines. They were very high-tech, very problematic, operating at the limits of what technology could do. And if you lost the main engine, you'd get to a low orbit. And if that happened, there were only two bad choices. One was to leave the Hubble in the cargo bay, and the shuttle would land at an emergency landing site, probably in Dakar, Africa, because that's the closest one. And the runway was, I think, dirt. In any case, the telescope would be thoroughly contaminated, have to be completely disassembled. And even the instruments disassembled, all the optics cleaned. Should probably take 5 years. It was never designed for this. So that would be a bad outcome. The other choice was to leave it in orbit and hope you could get another shuttle up in time to reboost it before it burned up. And if that happened, it also could danger to people because the mirror was big enough it would survive the re-entry, and it could hit a building or something. There's a lot of people living in that 28.5-degree latitude band. So someone had to decide this, and the powers that be said it was going to be me. So I did some calculations based on the swelling of the Earth's atmosphere and the solar activity, and made a little table and put it down in my lap, ready to do this. So I had to put on a headset and be in the blockhouse, and I've got a little control panel in front of me like this. In order to do this, even with my minor role, I had to go through simulations. So I sit there for days on end, and simulations mean every failure that could possibly happen. So it's one of the more depressing things I've ever done, is to sit there and experience every imagined failure for the shuttle. And so finally it happens, and Hubble takes off. And the everything works what we call nominal, goes in the right orbit, so I'm relieved. So I got on one of these airplanes. It's a shuttle training aircraft. It's a modified Gulfstream, and this is used to train the pilots to land the shuttle. An ordinary commercial airplane comes in with a 3-degree glide slope, a very precise 3-degree glide slope. It's controlled by these IL instrument landing system beacons. And the shuttle comes in at something like 40 degrees. So the way they simulate that, they take a Gulfstream, have it in flight, deploy the landing gear, put in full reverse, head the nose straight down to get them to train. So I'm on one of those airplanes going to Houston. Unfortunately, they flew it like a regular jet, didn't try and terrorize me. And this is mission control. I'm sure you're familiar with this if you follow this at all. I was not able to get on the floor for this because I wasn't trained for it, and I had no need to be on the floor. I had people in the back room, a big technical team. It's probably another building. They call it the back room. My people from my contractors, and I'm in a little VIP room with other VPs or companies and whatnot, CEOs. And people are coming in to talk to me about what to do. And the big problem was that the solar panels wouldn't deploy. They got stuck. And I was aware that they were a piece of junk. ESA provided them. I went and talked to the head of ESA and begged him to do a redesign. He refused. I had no leverage otherwise. And my safety and mission assurance team said that they didn't like the design either, but it'd probably work okay. So now the solar arrays won't come out. That's another big problem. So the people were trained well enough, even the people from Johnson, that they overrode it. The solar arrays deployed. And once we had electrical power, the thing turned on, the gyros powered up, and Hubble's in flight. So released by the orbiter that comes back to Earth, and everything's good. So it takes about, I'm thinking about 6 weeks before we can turn on instruments. And part of the reason is that there's high voltage. And when you have a vacuum, there's a period where if it's partially evacuated, the ions are very conductive and you can get sparks. So you got to wait until the thing gets thoroughly down to deep vacuum to turn everything on. Go out to Goddard Space Flight Center, which is the operations center. This is actually what it looked like back then. You can see how dated these are. Look at these monitors and computers and whatnot. So I had wanted to do this first light, it's called, in private, but at a press conference, they asked my boss, Lynn Fisk, if the press could be there for the first light. And he said, yes, so I'm stuck. So the aperture bay door opens, that sort of thing on the front. This image comes and everybody starts cheering. And I'm looking at this and I said, I've got my chief system engineer next to me. I said, Gene, these images they're blurred. They're not very clear. He said, don't worry. We didn't know how the truss was going to outgas in space. So we have a stepping motor on the secondary mirror that we biased a little bit out of focus. So we know if it's out of focus, which direction to turn in. We don't have to go back and forth. So it's all going to be okay. I said, okay, great. So I was exhausted. This simulations, all the press coverage around the launch, everything else. And as you people know, I like to go to these Rokons, these ends in Japan. And I had several international agreements with Japanese, and I had not tended to those. So busy with Hubble's launch. So I wanted to go over to Japan, and my colleagues know that what I like to do is go to one of these places where a foreigner's never been before. And this is, we've talked about this, this is what the room looks like. It's a Japanese style table, you sit on the floor. And they have a hot spring bath and a meal like this. This is a kaiseki meal, best meal in the world. So I go to my boss, Lynn Fisk, and said, Lynn, I'm gonna go to Japan next week. Looks like Hubble's all fine, and I need a break, and I like going over there. But in those days, we didn't have cell phones yet. We had pagers we wore on our belt. He said, you can page me, it'll work, but I have no idea how to call you from one of these Japanese ends. And maybe they don't even have a way to call the US, I don't know. So I'm gonna be out of touch, is that okay? He said, sure, no worries. And Lynn, being the nice guy that he was, that's actually a picture of him. We were friends. What can I do for you while you're gone? So I kind of laughed and said, there's going to be medals in the Rose Garden for Hubble. Would you make sure George Bush puts my medal on me and not Dan Quayle? So he kind of laughed about that, and off I went. So I had no communications for a week with anybody back in the US. I landed at St. Louis Airport. I'm in the red carpet lounge. I think it wasn't United in those days. I think it might have been even Pan Am. I don't know. St. Louis could have been a different airline. I decided to call Washington, see what's going on. So I called my office, my secretary, and she said, have you talked to Dr. Fisk lately? And I said, no. I'll put you right through. So I wondered about this, but I thought, usually you don't get put right through to an executive like that. It must be something important. So while I'm waiting for him to pick up the phone, I'm thinking it must be about the medals in the Rose Garden. So he says, Charlie, where are you? I said, I'm in the St. Louis airport. He said, what do you know about spherical aberration? I said, well, all I know about it is that when amateurs make a telescope and they grind the mirror by hand and do it sloppily, you get what's called a down edge. And so when the light comes off of the various parts of the mirror, it focuses at different locations on the optical axis, and the telescope is impossible to use. He said, you launched Hubble Space Telescope with a spherically aberrated mirror. This is 2 PhDs. I said, did not. He said, did so. I said, did not. He said, did so. That goes on for a while. He says, go put down the phone, don't hang up, and come back here with the front page of any national newspaper. So I come back with the St. Louis Times Dispatch, and he says, read me what it says above the fold. National disaster. Hubble launched with flawed mirror. Now what do you say? This is a true story. I said, how'd you guys get a fake newspaper into this lounge? You know, the Nile's not a river in Egypt. So he says, when are you going to be back in the office? I said, I can be back tomorrow. He said, well, be in my conference room at 7 a.m. Well, that was unusual. Work starts at 8 normally, and neither he and I would typically get up earlier than that. So I walk in there, and he's got all the top management sitting at the table. And I walk in the door. I know nothing about this except that I'd seen a videotape of the press conference left at my apartment. He said, how'd you let this happen? I have no idea what happened. They're just looking at me mad. So the meeting stopped, and Lynn said, come into my office. He said, we're going to have a failure review board for this. And if we let the Congress do it, they'll give us a lawyer for the chairman. And that's happened over and over. That's what Rogers Commission was a lawyer. And he said, we don't want that. So why don't we get ahead of them? How about Lou Allen, who was director of Jet Propulsion Lab? I knew Lou Allen, very fond of him. He's just a great guy. Was a 4-star general in the Air Force before that. And so I said, Lou would be great. Let's have him form the board. So he called Lou up. He started talking to his JPL people, and they got him some optics experts. So we went up to Danbury, the contractor plant, to have our first meeting for 3 days, and nobody could figure out what went wrong. There was a bunch of hypothetical theories, but one of them was that we should have done the testing in a vacuum, but this was completely mysterious how this could have happened. By the way, a little backstory to this. The original mirror blanks were built by Eastman Kodak, and they were pretty good. PerkinElmer had a plan to make them even better with a new computer-controlled method, and so we want to work at what's called the diffraction limit. So any optic has its resolution governed by a function of its diameter. And so when you're getting the maximum theoretical performance, the mirror is perfect. That's the diffraction limit. This is the first big telescope, maybe the last. We want it to be perfect. So we hired PerkinElmer to take the blanks from Kodak that were pretty good and make them perfect. That was what the deal was. So anyway, we still don't know what happened. And I'm summoned to Barbara Mikulski's office. She's a congresswoman at that time. And she's the head of the Appropriations Committee. That's the only thing that in Congress really does is the money. Everything else is pretty much noise. And the head of appropriations is a very powerful person, and she's mad. And the reason was that she'd asked me a year earlier, will it work? Now, if someone asked you, will it work, what would you say? Would you say maybe? Would you say, I don't know? After 15 years and $2 billion, it should be 6 or 7 billion today. What would you say? Nico, what would you say? Of course it works, gonna work.
Yeah.
I mean, you couldn't say anything else. So actually, I didn't know for sure because there's a key specification that is the stability that we couldn't test before launch. So I had my own misgivings about it, but I said, of course it's going to work. So let me explain what
Oh,
this technical requirement was. If you go up to where the night sky is dark, and there are places in Colorado that are very good for this, lots of them actually, dark sky places, and get a night with the moon's not there and it's clear, no clouds, you can look at and see something like this, and the brighter stars will be blinking. The stars are not changing. The stars are constant. What's happening is that there are variations in the intensity and in the density of the air that refract the light. So as the air has currents in it, wind is swirling around, the image is smeared out on the ground. So if you put a detector on the ground, you wouldn't see like point image, you see this kind of grayed out thing because the image is wandering around. Everybody clear on this point? Have I explained this adequately? Okay. So with Hubble, just like if you're gonna take a picture with a camera, you've got to hold the camera very still. Hubble above the atmosphere doesn't have any of that problem. That's the reason it's above the atmosphere, by the way, is because of that smearing of the image. So Hubble's got to be held very, very steadily. How steady does it have to be? Well, the specification is 7 milliarc seconds for 24 hours. Now, you probably don't think in milliarc seconds, so let me give you a metaphor. That would be like having a laser on top of the Washington Monument illuminate a pearl in New York City and never deviate more than 10 millimeters. This is hard, okay? Everything's that you've got some atmospheric drag, you got the torques of the solar arrays turning, instruments that got wheels moving. That's a very difficult thing. And how do you design a system to do this? And why? Because if you could make it really steady, that star would look like this. So how does Hubble see things that are much fainter than big ground-based telescopes, that big large ground-based telescopes can't see? The answer is it improves the contrast. If this mirror is perfect and hold it steadily enough, you get this. And it's equivalent of taking a factor of 10 improvement. So it's equivalent of going from legally blind, which is 2200 vision, to 2020 vision. Everybody got this idea that by improving the contrast, that's how you get more signal? Okay.
Yep.
So how do you do this? Well, it's called system engineering. So what you do is you make a computer model of the telescope, a big fancy spreadsheet sort of thing. You take each system that's involved with this. This is the carbon epoxy assembly that holds the secondary mirror. There's a secondary mirror. So the primary mirror is back here. Light comes in, bounces off of this, and comes down to the instruments. You take that and you put requirements on it for its stability, and then you measure it in a test chamber, and then you put its actual performance back into the computer model, and that'll tell you how close you are. Do that with everything that's involved with this, which is the reaction wheels, which is how the telescope turns, the gyroscopes, how it senses it's turning, the instruments that do take the data, the fine guidance sensors that make the error signals that govern all this, and the electrical components. You do this for every part of this, put it in your computer model, and at the end of the day, it should work. The problem is there's no way to test this. Obviously, what you would like to do is test this system on the ground. You hate to fly anything without testing. Test it on the ground, verify that it works. We couldn't do that. So had to depend on the analysis and the engineers. So anyway, she takes and puts her finger in my chest, and she's screaming at me. I've got spittle forming on my glasses, and says there'll never be an appropriated dollar to fix that telescope. This is a nightmare. It has to go away. What she's done is she's in the blamer state because she's mad because her choice to align herself with the telescope she fears will cost her politically.
What is now Diane Vaughan? Is that her name? The congresswoman.
No, that's Barbara Mikulski. Diane Vaughan is the author of the book about Challenger. This is Barbara Mikulski's her name. She actually became a senator lately, and a really good job as a a congressperson overall. So the NASA administrator was with me, the two of us only. He was a great guy. I couldn't find a picture of him looking angry, so I made one of these photographs and put this face on him. We got in his car. I mean, the administrator gets a chauffeured car to go places. He's got in his car to go back to the office. And he turns to me and says, "Charlie, you heard the congresswoman?" I said, "Yes, sir, I did." His name was Dick Truly, very friendly guy. I knew him sort of casually, but a good, also a Navy admiral previously. So I've got both the head of our appropriation, NASA administrator, telling me to leave this alone. So what do? I did this somatic psychology thing that I teach in the workshop. Go back to my office and sit down and said, "How am I feeling? Am I feeling lousy? Some kind of mixture of these emotions, mad, scared, and sad? If I am, I'm in a drama state. Which one is it? Breathe into this to minimize the emotions, get control of my body back. Look at the thoughts that are powering my emotions. The thoughts are, I cannot act because the Congress and NASA administrator forbade it. This is a state of victim. I can't do the right thing because someone's told me not to do it. How do you get out? You guys know, right? You shift the storylines. So address the unfortunate realities. It's a nightmare. It's not going to go away, no matter how much Mikulski wants it to go away. It's easy for Truly to fire me. I'm a member of the senior executive service. I don't have much civil service protection as a senior executive. There's no way, there's no idea for a technical fix. Nobody had any thought about how to do this. People have been working on this now for about 3 weeks. This board, this smart people, optics people that built it, nobody knows anything how to fix it. And the truth is that I'm the only person that can fix it. I'm the only person that has the motivation and access to resources and the authority to direct this. So there's no remedy except the space repair. That becomes obvious to me. The greatest mantra in the world is "so what?" So they might fire me, so what? Need to look deeper. I need to 100% commit to this. So in this drama state, I cannot attempt to fix the telescope. I changed the storyline to a green one. I must fix the telescope. I can fix the telescope, even though it's not clear how. I will fix the telescope. So this is that place of complete focus where that's all you see is what you got to do, the action, nothing else. We'll talk about this more later, but you might remember the baseball analogy with the pitcher looking at this material before. So we're in that state. All you see is the need and way out. Here's some tests before you.
Charlie, do you want to break here?
We can now. I was going to go to this slide, but let's go.
Sorry.
On your feet. Okay. So I wasn't this formal with this, but thinking about this later, I thought if you're going to consider committing 100% to something, these are the questions that I recommend that you ask. The first one is it the right thing to do? And what this is about, if it's about you, it's not. If it's about a higher purpose, that's the test. Whose interests are being served, sort of the same idea. Are you competent to do this? Well, yes, I am. I'm got the right education, PhD in physics. I've got the right management experience. Yes, I'm not only am I competent, I'm probably the only person that could do this. So become 100% committed. And people say to me, what a great thing. No, I like this quote from Admiral Bill Halsey, a famous admiral during World War II. There are no great men, just great challenges that ordinary men out of necessity are forced by circumstances to meet. That's how I look at it. So I called in my budget analyst, a good friend of mine, Greg Davidson, and I said, Greg, I want to reprogram some money. I want to put $60 million in a secret fund. And you can't tell anybody we're doing this because I've been forbidden to do this by both the head of NASA and the head of Congressional Appropriations. And I said, if anyone asks you, if we get caught doing this and someone wants to punish you, I'll say I made you do it. He said, don't worry about that. Meanwhile, a group out at Goddard had done the Solar Max repair mission, the only space repair ever done by a very superb manager leading that group, Sepolina. Call these guys up and said, I've got $60 million to fix Hubble. And I've been forbidden to do this by the head of NASA and head of appropriations. Will you start work on this and not tell anybody? And they said, sure. So meanwhile, Ball Aerospace VP is coming once a week to meet with me and talk about this. They designed and built all the Hubble instruments, so they've got deep optical expertise. And a friend of mine, Jim Crocker, who's at the Space Telescope Science Institute, also is an instrument wizard. And they come to see me one day and said, we found a way to fix it. And the idea is that we're going to take out one of the instruments, substitute this thing, got little tiny mirrors. And the big question is, how are we going to hold the mirrors? And Jim says, I was trying to figure this out. And I was in the Millennial Hotel in Boulder. That's Ball Aerospace is in Boulder. And I looked at the shower and saw how the shower head went up and down and said, we can do the same thing with these mirrors, put them on a screw drive, a digital motor, just like the shower head. So now we had a solution. So for many years, I was upset with Mikulski over this. And some years back, some friends of mine at Goddard said, actually, Charlie, if you think about it, she gave you a great gift because the gyroscopes were failing. Right now, Hubble's got the same problem. It's down to one gyroscope working now. It can work, but at limited capability. The gyroscopes were all the older version then. And if she hadn't said that to you, if she had said, for example, go put together a plan and I'll deal with it in the budget, that would have delayed everything at least 2 or 3 years because I would have to go do the studies, build the evidence package, get it through the NASA management, get it to the Office of Management and Budget, get it to the Congress, get it funded. Hubble would have been gone. So she actually gave you a great gift by what she did. Hubble would be tumbling, and once it's tumbling, it's too dangerous to go close to it with the shuttle orbiter because this is all very fragile stuff. Meanwhile, I'm talking about this at the 25th anniversary, and a guy, David Frigurio, a screenwriter, contacts me and says, I want to write a movie about, he saw me on the, I think probably this National Geographic thing. He saw it, I think in the airplane. I want to do a movie about you. And here's the sizzle reel for the movie. I have to, sometimes it loses sync. Let me see here. Trying to get to share the sound. It's okay.
Just say no.
Where's the beat?
Space Shuttle Challenger is just a few seconds away from blasting off from the Kennedy Space Center near Cape Canaveral, Florida.
What's happened? What happened? Everybody here is open now.
Controllers here looking very carefully at the situation.
We mourn their loss as a nation together.
Challenger was the 51st shuttle flight. And NASA marketed the thing as routine space access and believed it erroneously. What do we do now? And we didn't know. I'm Dr. Charles Pellerin. I led the Hubble Space Telescope development program for 8 years. I think we may have been 6 months out when Challenger happened, and we got a now delay. I don't think you could find an astronomer or an astrophysicist who wasn't excited about Hubble. It's clear it's going to be a big deal. I wanted to have a low-key launch. I wanted to kind of quietly launch Hubble and make sure it worked. And this was a joke. 3 months before the launch, people are already lining up at Cape Canaveral getting ready for this. The Hubble family's out there selling their electrical connectors.
Dr. Pellerin, you've been involved with this project for 8 long years. What are your final thoughts on this night before we all hope that telescope goes up into space?
Well, Chris, I think I feel like people must have felt when they saw Columbus sailing off to discover new worlds.
It goes back to Jules Verne. You know, the idea of a telescope in space is something that just has a lot of appeal to ordinary people.
10, 9, 8, 7, 6, start, 2, 1, booster ignition, and liftoff of the Space Shuttle Discovery.
Hubble finally launched in April 1990.
Hubble telescope, the greatest telescope since Galileo invented the first one.
All NASA top management's in this conference room, and I walk in there and they're all mad and said, "How'd you let this happen?" I have no idea what happened. Zero. Well, you launched Hubble Space Telescope with a flawed mirror. And I said, this is 2 PhDs. I said, did not. He said, did so. Did not. Did so. Did not. Did so. I said, okay, stop. Just stop. I could not believe it. I was really in literal denial. So spent the first 3 days and nobody knew what happened. Nobody could figure it out. The Congress has these hearings. Now hearings, no one's hearing anything. They should better be named as browbeatings or something, or bashings. So I get summoned to Barbara Mikulski's office, and she's mad. Barbara Mikulski was a congressperson at the time, and she was the chair of the Appropriations Committee that dealt with NASA's money. That's a more powerful job than being an administrator. She decides what money we get. So I walk in there, and she throws newspapers at us, and then she sort of starts screaming at me so much that spittle is forming on my glasses. She takes her finger and shoves it in my chest and says, there'll never be an appropriated dollar to fix this telescope. This is a nightmare that has to go away. My first thought was, I can fix the telescope. And the second thought was, I will fix the telescope. We were all on fire. You couldn't keep us out of the office. Nobody had time for nonsense and review boards. You're not allowed to do this. I can't just give someone $50,000. I gotta go with a competition and a peer review process. I ignored all that stuff. I said, 50 grand, you got it. The images just blew people away. In our imaginations, I think we all saw maybe some astronomical image in a textbook or something, or a movie, and thought, well, that's kind of interesting looking. But the Hubble images were mind-blowing. Hubble was great science, but it did more than that. It took the whole world on the journey with it.
Well, the movie ran into COVID, got stalled out, and recently someone's got interested in it again. We'll see. And this is another clip. I'm going to skip that. I'm going to get these fixed better. So let's look at what happened. So the mirror was 2.4 meters or 96 inches in diameter. And this shows the intended state is this brown line. The actual mirror was misshapen it was perfect at the center. The error got worse and worse to 4 microns at the edges. That's the maximum error. How big is 4 microns? Well, a human hair is 75 microns. So it's a small fraction of the width of a human hair. And it's not something that you could see except with optical instruments, and it wouldn't matter for anything other than a telescope. So how bad was the impact? This is what a ground-based telescope could do in a nearby galaxy. This is Messier 100, M100. That's a good ground-based telescope. This was the best Hubble could do. I was responsible for the biggest screw-up in history of science. So what happened? You think it was technical or social? I know you guys know better, so it's a rhetorical question. But what quality of people do you think applied for jobs on Hubble? Best in the world. When you had any kind of an application for technical people, you got top people. Scientists wanted to be part of this. What occurred was that the remanufacturing of this mirror used this device called a null corrector to make the optical image that would be the guidance for the polishing. Normally, you would space this with special micrometers, but in the case of Hubble, because we're making a perfect mirror, we had an INVAR bar you put in the center that came from the Bureau of Standards that tried to make the thing perfect. We made a 60-inch mirror with this device, and the mirror was tested and tested. It was absolutely perfect. We got to the changer for the 96-inch mirror. You only had to do 2 things. Put a different INVAR bar in here and put a little field lens on it. Well, the instructions said to take the bar and put a little aluminum cap on it that you'd sprayed with non-reflective paint. They're behind schedule, they're working at night, they're in a hurry. Guy couldn't find the paint, so he put a piece of tape on it. He took his X-Acto knife and cut a hole in the non-reflective tape. He didn't notice that he chipped the tape and there was a little edge where it was still shiny. So you put this in here and you put a laser in here, and the instructions were to turn these knobs and space this thing right and left. And it should be in a place where any turn off gets it to be weaker. So it goes down into the center of the hole, gets weaker, off to the sides of the tape goes weaker. So it misspaced it by 1.3 millimeters, which was the height of the little cap. So that wasn't the worst of it. That we finally understood. What was more perplexing was that when you took the mirror and put it in the flight mount, like here it is being tested and here it is up on the flight mount, we had to use a different device to measure it, similar but refractive null corrector, and it showed a half wave of error. And the engineers at PerkinElmer saw that and should have said, wait a minute, let's go do some more testing and find out how this mirror could be out of spec. At that time, PerkinElmer was overrunning and overrunning. There were lots of pressure, and the only tangible progress the project could point to, it's like in its 6th year now, is this mirror. So the idea that the mirror would be flawed and have to be taken down and redone was something almost inconceivable. They did what technical people do. They did a calculation that said, let's treat the mirror, it's a very difficult calculation, let's treat the mirror like it's a liquid, and at some level glass is, And if we take it out of the zero gravity mount and put it in the flight mount, calculate how much it will sag under gravity, they kept tweaking until they got 1 point, half a wave of error. So they assumed that the mirror was perfect, but being distorted by gravity in this mount. This is a common thing. It's called confirmation bias, and we all do this. It's dangerous. What we tend to do is we tend to select the information that matches our preconceived notion and take it as truth. Everybody clear on what we're doing here? Confirmation bias?
Yes.
So here it is. Here's the engineer's mindset. The mirror couldn't be bad. The objective reality, the overlap is in this calculation, which says, wait, it's the problem is the mirror is flawed, but it's flawed because and being distorted by gravity. And they withheld, this happened in multiple places in this process. They never told NASA. This is what shocked the failure review board the most. What happened was we had a social context of hostility and blaming driven by the multi-billion-dollar overruns that made them reluctant to mention any problems that might not be real. And we had lots of problems that were real. So that's the environment in which they withheld it from us. Lou Allen was the director of Jet Propulsion Lab, which is a NASA center in some sense, but it's also a contractor. It's kind of an ambivalent place. And he had seen the abuse of NASA managers when they had technical problems. He understood this phenomenon. If it had been a NASA review board, this would not have been the finding. But because it was Lou, when he went to told the Congress how he spent 15 years and $5 billion and has built a useless telescope, the root cause was a leadership failure, and I was leader of the team. So what happened here? Social diagnosis. Behavior driven by desire to avoid criticism. It's a social context failure. You may remember early on I mentioned John Mather, a scientist for this project, brilliant physicist who got a Nobel Prize, said, Charlie, I'm convinced that half the cost of our project is socially determined. He brought this whole idea back in my consciousness. I just must say that nobody blamed me, and nobody in NASA blamed me. Mikulski blamed me, but that's just politics. Because nobody saw anything I'd done wrong, and I was pretty well respected as an effective manager. I think you can imagine what the aftermath was like. I won't give you any details, but I didn't read newspapers, didn't watch late night comedy. I decided it was safe after a couple of years to go watch Naked Gun 2.5. And they're in the Blue Note Lounge, and they're talking about disasters, and the camera pans across the back, and they've got a picture of the Titanic sinking, Hindenburg on fire, and the artist's concept of Hubble used to hang in my office. There was no escape. I'm happy to say that when I put together the team for the servicing mission, I already knew about the power of appreciation and said, we're going to appreciate more than we criticize. And because I knew this team had to do better. It's a much more complex thing. And so, and we also need to be 100% committed. And anyone that doesn't show this, I'm removing. And I removed 2 managers. So the management team that I had was already heading towards 4D. So does your organization reward people for fixing problems they created? NASA does. I got promoted up to the top of NASA. I'm like the number 3 person. I hate it. It's all politics. First time in my life, I didn't know what to do with myself. So I ended up getting a sabbatical and going to the University of Colorado and teaching in the business school and watched the successful repair. There were so many naysayers that people wrote books about our failure and planned to get rich selling them. But the team that I put together hung in for the whole 2.5 extra years, and the thing exceeded everything. So let's look at a few of my favorite things. It confirmed the existence of supermassive black holes at the center of galaxies. Confirmed the accelerating expansion of the universe. This is a very peculiar result. So when I was in graduate school, we believe that the universe, we knew it was expanding from the Big Bang, and the current prevailing thinking was it was collapsed back in on itself, just like when you throw a ball in the air. You start with lots of kinetic energy, it converts to potential energy, and the ball comes back down. This would be like the universe started to expand like the ball going up, and then after about 4 billion years, it accelerates and runs away from you. This is called dark energy, and nobody knows what this is. And this is one of my favorites. This is an image of a supernova. You can see this with a small telescope. It's called the Crab Nebula supernova in 1054 that lit up the sky as bright as sunlight during the nighttime. Now let me talk a little bit about this. This is kind of fun. So the Big Bang just made hydrogen, helium, a little bit of lithium. Where did all the stuff we're made of come from? The answer is it was formed in these exploding stars. So stars are trying to gravity's forcing the star to condense, and thermonuclear fusion is creating heat to push the star back out. It's burning fuel. So when the star is pretty big, and finally the fuel's exhausted, it explodes. And that explosion is where it makes everything that we're made of. So in this vicinity of the universe, there had to be sort of half a dozen supernova that happened to create the elements that later condensed in to form Earth and people and desks and chairs and matter. And everyone's favorite is so-called deep field. This is a view where the sky is completely black to ground-based telescopes, never anything seen. It's pretty small. Its angle of a tennis ball makes it 100 meters. And the director of the Institute stared into this for 2 weeks with Hubble against the science community's wishes. And he saw this. Every one of those dots is a galaxy. And a guy named Eric Whittaker wrote a symphony that's not playing, but doesn't matter. And this immediately created our sense of how many galaxies there are by a factor of 10. So the universe, wrap your brain around this, 2 trillion galaxies, each with 100 billion stars. That's the visible universe. So that wraps up Hubble. Let's have some conversation. We got 5 more minutes. What anybody thinks about all this? What did you get out of that example? Was it useful?
Hi, Charlie. So what I wanted to actually understand is when you say earlier at the beginning, you were talking about we knew how certain things work. Like,
yes.
But then later on you said, well, many things you actually couldn't do it unless you are in space. So
yes,
like what is how do those things connect? So were there actually many things in the process where you just do scientific analysis calculations and then you go with your best estimate? So then how does that really relate to decision making, to management and all of that?
So you're talking about the stability thing that I described and how I
Yeah.
couldn't be sure it's going to work.
Yeah.
The thing is that we can do it analytically. We can do a computer model and convince ourselves that it's right. And what you'd like to do is do all that and then test it. So for example, if you're going to build a rocket engine, you do the same thing. You do all the analysis. You build the computer thing. You do all the equations. In the end, you'd like to put it on a test stand and light it up and make sure it works.
Yeah.
So the problem with Hubble is we did all this stuff engineers always do. Very complex system, many moving parts. It's a very systems problem because it's every piece of it interacts. What we would like to have done is find a way to hang it up in a vacuum chamber somehow and hold it there and put a target star, turn it on and see that it functioned. We couldn't do that. So we had to count all analysis. And you can be pretty sure, but rocket engines explode on test stands, things go wrong. The point is that I had confidence in our engineering. I wasn't worried about that at all. But without a final test, you never can be sure. That's all. It's a matter of confidence. Couldn't test it. And so what I worried about was that stability. That's what I That's so hard, that's so technically difficult, that is the most precisely pointed thing anyone ever made ever. And if we missed it by a factor of 10, we still have the most precisely pointed thing anyone ever made ever, and the telescope would be useless. So I worried about that problem a lot because I could never be certain. It's all, you know, mathematics and modeling is great, but you sure like to know for the test. That's all. It's a matter of confidence. I knew in my heart of hearts it's going to work, but there's always this nagging doubt if you can't test it. That's really what it amounts to.
Yeah. Yeah. So it's like, I know you speak often about unfounded reality and
Yeah,
about those things.
unfortunate realities. Yeah. So we just, I mean, it's like one of Nat's solar systems. You can put it all together, but until you turn the switch on and see if it operates,
yeah,
you don't know what you've got, no matter how careful you are. So, you know, even something as simple as wiring a house, until you turn the power on, you don't know for sure. You know, and this is so complex, and the reason it's complex is that everything is interacting on this. My point is that if you want to hold it steady, you got to worry about when the solar array is going to adjust. That puts a torque into it. That can't happen while you're taking data. You got to calculate, for example, the capacity of the gyroscopes to be able to change their speed accurately enough that it does it completely smoothly and holds it in place. And it actually more complications. You slowly build up momentum, so you've got to use magnetic torquer bars to dump the momentum back into Earth occasionally. So there's a lot to it. That's all I'm saying. And the fact that I couldn't do a test beforehand, always had this nagging doubt that you know.
Thank you, Charlie. It was an amazing session. My apologies, I've been a few minutes late. I was doing Tai Chi, and when I'm doing it, I'm taking my watch out and I completely got lost really track of time. So sorry about that.
So we'll have it open, think about what we learned from this example, and we'll start next week talking with you guys, talking about it. I want to know what your takeaways were from this example.
Sounds great.
In terms of the social context, more than the Hubble technical details, perhaps.
Thank you, Charlie.
Thank you all.
Thank you.
Have a great week. See you next week.
Thanks, everybody.
Bye-bye.
Bye-bye.